All right, guys, had a few quick questions about piecewise functions and continuity. So here are a few piecewise functions, and notice a few key pieces of information are missing. So we have a piecewise function defined as 3x squared for x greater than or equal to 1, but we have a incomplete linear function here for x is less than or equal to 1. And so the question here specifically is find the constant a such that the function is continuous over the real number line. So we know linear functions are continuous. We know quadratic functions are continuous. But the only question is where these two things meet, we need to make sure they meet at a single point so that the entire piecewise function is continuous. Likewise over here. So here we have three functions. We have the constant function -2 for x greater than equal to 3. We have the constant function 2 for all x values less than equal to 1. But here in the middle, this says, hey, we need a linear function. Ax plus b is a linear function so that we connect those two horizontal lines so that the entire thing is continuous. So really you should draw a graph to visualize what's going on in both situations. And we might do a couple more. We'll see what time allows. So let's draw a Cartesian coordinate system. Just our two number lines. Okay, now what we're going to do here is start with the piece we know about. 3x squared. We know how to graph that. Okay, that's a quadratic function. It has a vertex at 0, 0. This is just stuff that you should remember from algebra class. And then that 3 is just going to stretch it a little bit. That's all. So we have a vertex. Let me change over to a new color. Let's do this in purple. The vertex is at 0, 0. Now let's just pick another point on the graph. If you plug in 0, the y value is 0, so 0, 0 is there. If you plug in a 1, you get 1, 3. So 1, 3 is on our graph. And if you plug in, let's say 2, you would get 3 times 2 squared, so you get 12. So that's way up here. So 2, 12 is a point way up here. But essentially, what this looks like is so. Now, if we were going to draw the entire parabola, it would look like this. But that entire parabola is not defined in this piecewise function. This piecewise function only says, hey, draw the parabola when x is greater than equal to 1. So I have to erase everything that is not above an x value that is 1 or bigger. So I erase all of that. So the parabola, we erase everything except from 1 and to the right. And we do signify for the time being that f of 1 is 3 in this case. Okay, and now we have this other part to deal with. So here's half of our piecewise function. From 1 and to the right is defined by that purple line. Now what about this part on the bottom? It says essentially we have a linear function where the slope is unknown, the a is the slope there, and the y-intercept is -4. That's in y equals mx plus b format. So we know that -4 is our y-intercept. So let's draw this in a different color. So there's the y-intercept of this new linear function. But we want to make sure that we have a line that passes through that y-intercept but also connects to this point right here. Now, we know this point is 1, 3. Okay? So to get a line that has this y-intercept, which indicates by this, it's indicated by this, we can simply do a little bit of algebra. We know that we need the line that passes through, well, 1, 3 and 0, -4. Okay, so that's just, that's a classic problem from, college algebra or maybe even intermediate algebra. We first need a slope. We then need to find the equation of the line via point-slope form, and then lastly, we need to convert it to y equals mx plus b slope-intercept form. So let's see. Let's label our points. Let's call that x1 and y1, x2 and y2. So m equals y2 -4 minus y1, which is 3, over x2, which is 0, over x1 minus 1. Okay, so we have what? -7 over -1, which equals 7. So that is our slope. Okay, now that we have a slope, we can use, let's just use this point, since it's already labeled as such, into point-slope form. Recall point-slope form as follows. Y minus y1 equals m times x minus x1. So plugging in, we have y minus y1, which is 3, equals m, which is 7, times x minus x1, which is 1. That is the equation of the line, but we need the equation of the line in y equals mx plus b point-slope form, because we're looking here specifically for a. We already know what b. We already know what the b is. It's -4, but we just need a. So let's see. Y equals 7x minus 7 plus 3. So y equals 7x minus 4. So there we have it. Here is the A we're looking for. Okay? Because this is the line, and I'll draw the line now, that passes through 4 and connects to this point. So let's see, I'll try to freehand it. Oh, that's not a very good line. It'll get the job done. Okay, so this is a continuous function now. We have a linear function over here. Then we have this part of a parabola in purple. They connect at the point 1, 3. So we know this blue is continuous. It's a linear function. We know the purple is continuous. It's a quadratic function. The only question was we have to make sure they meet at a single point, so there's not a hole or a jump there. And doing these calculations, we did just that. So we can go back over here and say the missing piece was simply a 7. And now that is a function that's piecewise and continuous everywhere. Okay? This one takes the exact same idea, except now it's piecewise in 3 parts. So let's take the 2 parts on the end. Let's first, draw a graph. Okay, this says for all x values less than or equal to -1, the y values are 2. So let's say there's -1, -2, -3, -4, etc. All of those x values have a y value of 2. So let's see, 1, 2. So there's a y value of 2, a y value of 2, a y value of 2. So you see we're going to get a horizontal line, like so. Actually, Let me change colors real fast. We're going to get a horizontal line like so. Now it says when x is less than or equal to -1, so we'll put a solid dot there for the time being. Now let's go over here. This says for all x values greater than 3, we're going to have y values of -2. So we go over here, say 1, 2, 3, 4, 5, 6, let's say. Well, for 3 or greater on the x-axis, the y values are all -2. So we'll make this in purple. So 3, -2 is on our graph. 4, -2 is on our graph. 5, -2 is on our graph. And so we have a horizontal line at -2. And so the question is, what goes in the middle such that this whole piecewise function is continuous? Okay, now, in reality, there's lots of different options, but this is specifying a linear option. You know, we could figure out a quadratic function that bridges this gap. We could figure out any number of different types of functions that would bridge the gap. But we want the linear option that does it. That is, we want the line that connects these two dots. Well, just like last time, what are the coordinates? Well, that's 3, -2. And this one is -1, 2. And so we need the line that connects those 2 points. So just like before, we'll do the exact same process. Label your points, apply the slope formula, apply the point slope formula, then convert to slope-intercept. So let's see. We have, let's see over here, we have -1, 2, and we have 3, -2. Let's label the points. x1, y1, x2, y2. So m equals y2, which is -2, minus y1, which is 2, over x2, which is 3, minus x1, which is -1, equals, let's see, that's -4 over 3 plus 1, 4, equals -1. So the slope we're dealing with is -1. Now let's use point slope form to write the equation of the line using the same x1 and y1. We could use these points, but these are already labeled appropriately. So y minus y1, which is 2, equals m, which is -1, times x minus x1, so minus -1 plus 1. So y equals -x minus 1 plus 2. Y equals -x plus 1. So here is the linear equation that makes sure we bridge this gap without any holes or jumps. So specifically, A equals -1 and B equals 1. So going back over here, we could say the continuous function -x plus 1, or the function -x plus 1 fills that to make the entire piecewise function continuous. And so this actually looks like it makes good sense because we passed, this has a slope of -1, y next to the +1, and looks like that works out just perfectly for us. So we have 3 linear functions, well, 2 constant functions rather, and a linear function. They're all connected perfectly so that the entire function is continuous. Okay? And the rest of the homework problems are similar. I'll pick one of the harder ones now and see how that works. But this is how most of that section works. You're just trying to figure out what linear function, or maybe what other type of function, bridges the hole or the gap that was in the graph originally. Let's take a look at one of the harder ones. All right, let's see what we might have here. All right, let's see. 68 looks like it's one of the harder ones. 68 says this. We have on the bottom natural log of x minus 3 plus x squared. That's valid when x is greater than 4. And then we have 2 times e to the ax power minus 2. And that's valid when x is less than or equal to 4. So let's start with the piece with no a's in it. Like, that's just a complete function. There's nothing missing in it. So let's see what the graph of that looks like. Now, here's the thing. I have no idea what that graph looks like. Well, I know that there's an asymptote here at x equals 3 plus x squared. That's kind of strange. Here's how we can do this. Let's just make a quick table real fast. Of course, if you had a graphing calculator or software, you could get a better idea. It doesn't really matter what's going on here. What matters is that when x is greater than 4, there's no problems here. There's a problem at 3, because if you plugged in a 3 there, you'd have natural log of 3 minus 3, natural log is 0. Okay, that's a problem, because there's an asymptote in this function at 3, but it's not defined for 3. It's only defined for greater than or equal to 4. So let's just get an idea of what the first couple of values of this function look like. Let's just plot a few points. For instance, if we plug in a 4, okay, now 4 is not in the domain of this function, but let's just say it was, what would it look like? Well, it would look like, okay, let's plot it. 1, 2, 3, 4. It would be natural log of 4 minus 3, which is 1. Natural log of 1. What's the natural log of 1? Or what's the log, any base of 1? It's 0. So it would be 0 plus 4 squared would be 16. So if this was defined for 4, you would have, okay, I'm going to have to truncate the scale here. Let's say that's 16. We would have this point. But, this function's not defined at that point. Okay, I want to be clear there. This function is only defined for points to the right of 4. I'm just trying to get an idea of where this function, what it looks like over here, because I have no idea off the top of my head. Okay, now let's plug in, let's say a 5. Okay, let's see what the function looks like at 5. Well, you would have natural log of 5 minus 3, which is natural log of 2. So natural log of 2 plus 5 squared. So natural log of 2 plus 25. Okay, so a number a little bit bigger, a pretty small number, but a little bigger number than, let's see. No, it's a number smaller than 1. Okay, natural log of 2 is a number smaller than 1. But plus 25, you're going to have a number way up here. So it's like off the board. So at 5, this is off the board. It's getting really tall really fast. So it's like this. Not straight up, but it's going really high really fast. Okay? All we need to know, really, is it's getting really high. It's increasing, but it's continuous. There's no problems here except when the argument turns negative or 0. But if x is greater than or equal to 4, no problem. So that's all we need to know. All right? But now let's think about this. So this is a exponential function, it's going to be defined all over here. So from 4 and to the left. We know that it's going to look something like this. Let's see, it's -2, so it's been shifted down. So it's going to be something like this. We need to connect them. But we need, if we just pick any exponential function, they might miss. It might be like this. If we just pick just any old exponential function, it might go like this. And so they miss each other. Okay? So we have to make sure that whatever exponential function we pick actually connects to that dot so that there's no gaps, there's no holes or anything. And here's how you have to think about it. We want the exponential function to have a specific point. What is that specific point? That point is 4, 16. We want this point to be on that function, and that's going to be the key to solving this problem. We're going to try to find a. We just need to find the value of a that makes an exponential function connect to that dot so that there's no holes in the graph and there's no breaks in the graph. So let's for just a moment say g of x equals 2 times e to the ax power minus 2. If we want this point to be on g, then we could say g of 4 equals 16, which equals 2 times e to the a times 4 minus 2. This means when you plug in a 4, the answer is 16. So all we have to do is solve this equation for a, and that will give us the value that gives us the exact exponential function with those parameters that connects to 4, 16, which makes this be a smooth continuous curve. So let's see. Now this probably gives you flashbacks to algebra class. If we want to solve this, we have, just off to the side, 16 equals 2e to the, let's just say 4a minus 2. Now the first thing you want to do is try to isolate your exponential term. I would divide everything by 2 probably first. If you divide everything by 2, you get 8 equals e to the 4a minus 1. Okay, now we're going to try to isolate the exponential term. So we add 1 to both sides. 9 equals e to the 4a power. And now whenever you're trying to solve exponentials in this form, you take the log of both sides, or we'll take the natural log, so it'll be a little bit easier. So we take the natural log of 9 equals the natural log of e to the 4a power. The reason we did that is because now we can rewrite the right-hand side. So natural log of 9 equals 4 times a times the natural log of e. Okay, that's just using the properties of logarithms. But now we know that this simplifies. That is equal to 1. Natural log of e, log base b of b is always 1. So this is log base e of e is equal to 1. So to solve for a, we just divide by 4. So natural log of 9 divided by 4 equals a. And that's all we need. Okay? If you go back up here, we can write natural log of 9 over 4 times x. That will give us an exponential function. Okay, it's going to be an exponential function that's shifted down 2 units. It has a horizontal asymptote down here. Okay, it's going to cross the x-axis. Well, what happens if you plug in a 0 for x? You get e to the 0, which is 1, and then 2 times 1 is 2 minus 2. So it crosses the x-axis at the origin. And so we have an exponential function like this, which connects at that dot perfectly. So now we've connected this function and this function. We know individually natural log is continuous, x squared is continuous. Well, okay, natural log is continuous over its domain. X squared is continuous everywhere. So this is continuous for sure for all x greater than 4, so that the sum is continuous. Exponentials are continuous over their entire domain of real numbers, so this is continuous. The only thing we weren't sure about was that point where they were going to connect. We had to ensure they connected at that single point and there wasn't a gap or a hole there, and we have successfully done that by ensuring the correct value of A. Okay, there's a handful of other problems in that section. I think this is probably one of the hardest ones, so hopefully the other ones are easier, especially like this. Those ones are a lot easier where you're just doing linear functions. If you have any more questions, feel free to ask on Blackboard or send me an email or whatever. I prefer to ask on Blackboard, and I'll be more than happy to help you out. All right, so we have a hurricane coming, so be safe out there, and we'll talk to you soon.